So again, hopefully you're finding that fourth page on your packet and you have on your periodic table. I have up on my first slide, what do we have to go over today? We need to go over the D and the F orbitals, and I'll show you that on the periodic table again here in a second to remind you of those. Neutral atoms, meaning same number of electrons as protons. And then there are two interesting twists dealing with those D and F orbitals. Half-filled orbitals is something we have to go over dealing with stability. And then how do they form ions? So that's our goals for today. The good news is I already taught you orbital notation, electron configuration, and the shorthand notation. I'm not teaching you any new ways to draw it out. We're just doing the same methods for bigger elements now. Okay, now, today we are talking about that D orbital, which is in the middle of the periodic table, and the F, the bottom. However, what you're going to learn today is that the D and F are a little wonky. So, recall that you wrote down numbers 1 through 7 on the left-hand side of your periodic table, correct? I want you to do a little writing on your periodic table right now, and I'll explain why later. Between calcium and scandium, between elements 20 and 21, I want you to write a 3 in between those two. So that's what I'm showing right here. Between strontium and yttrium, I want you to write a 4. Between Ba and La, a 5. And between Ra and Ac, a 6. And make it noticeable enough for you to see. Now, what some students like to do is, if you get to the end of the D orbital, they like to number back the way it was before. So, for example, next to boron, they sometimes will write a big 2 to remind themselves, hey, that is the second energy level. Next to aluminum, write a big 3. Then between zinc and gallium, between elements 30 and 31, write a big number 4. That fourth row across is when things start to get unusual. Then a 5, 6, and a 7, bless you, to get down to the end of that row. Again, that fourth row across is the start of unusualness with the periodic table, which is why we only went to calcium last time. Last thing to write down, that F orbital is at the bottom of your periodic table, those two cutout rows. I want you to write a 4 and a 5 next to those two rows. 4 and a 5 next to the bottom two rows of the periodic table. So again, hopefully then your periodic table looks somewhat like this. Again, maybe you did a little bit better job of highlighting or outlining, but we need to know the S, the P, the D, and the F, the 4 orbitals, and we need to know the energy levels, which is the numbers that we have written on that. And our goal today is to start doing larger elements than just calcium. But that's when things get a little tricky, which is why we have to go over these exceptions as well. Okay. On your note sheet, and on my slide here at the bottom, is a picture of the D orbitals. The D is when things start to get a little tricky. Notice that there are 5 suborbitals for the D. And what makes the D interesting is that the D orbital is so large that even though it starts in that 4th row across in your periodic table, again, you have a big number 4 right next to potassium. You go potassium, calcium, then scandium, it enters the D. Even though the D starts in the 4th, it's so big with those 5 suborbitals, it actually overlaps with the previous energy level, the 3rd, which is why I had you write a 3 next to scandium to show anything from scandium to zinc actually occupies the 3rd energy level, even though it's in the 4th row across. Again, that is kind of an unusual thing for that. Now, before we do this practice problem that I'm saying up on the board here, in your note sheet, you have another table that says number of suborbitals and number of electrons when full. We've already stated that there are 5 suborbitals in the D. Look at these 5 different shapes. How many electrons can fit in a suborbital? Do you remember that from last class? How many arrows? 2, right? So how many electrons can make the D completely full? 10. Look at your picture for the F. How many suborbitals do you count for the F there on your sheet? 7. How many electrons then? 14. Again, the shape of the periodic table has everything to do with this. If I went from scandium to zinc, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements corresponding to the 10 and the D. The F orbital at the bottom, 1, 2, 3, touched it on too hard. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, we should be able to map out any element on the periodic table based upon this. Okay, so what I'm going to do right now is the orbital notation for nickel. Remember, orbital notation is the up and down arrows. Every element starts the same way. Innermost shell is the 1s. Then comes 2s. Remember, the first arrow up would be for lithium, the second arrow down would be for beryllium. The 2p will be completely filled. That'd get us to neon. (3s) filled would get us to magnesium. (3p) completely filled would get us to argon. I'm running out of room, so I'm going to go down a line. I'm going to stop at calcium for a second. Calcium is element number 20. This is what we stopped at last class. Now we're going to enter into the transition metals. We're asking you to solve for nickel. So the first thing to note is when you go from calcium to scandium, you wrote a big number 3 in between those two. Because we're no longer actually in the 4th energy level, which is a little weird. We're in the 3rd. Next, that dip in the periodic table shows the d orbital. So I need to write 3d. I need to show all 5 suborbitals. 1, 2, 3, 4, 5. Then I count. What element is nickel in the D? 1, 2, 3, 4, 5, 6, 7, 8. It's the 8th element. Now remember, how we fill is with individual ups first. 1, 2, 3, 4, 5. Now we double up and flip the spin. 6, 7, 8. This is the orbital notation for nickel.
After 3 using it, go back to 4 then.
If we did go to, it's a good question that Connor states, is if we did get past the 3D and we went to say bromine, it would go back up to 4P, yes. Which is why I wanted you guys to write a big 4 between the zinc and the gallium. So again, through calcium, there's a nice even pattern. And I'd say there's still a pattern with what we're doing here. It's just that you got to read your periodic table, folks. Because that's going to help you out. And that's why we wanted you to write on your periodic table, to use this as a tool. Okay, so hopefully that is an explanation of entering the D. And it's also going to be a reminder of orbital notation in case that is something that you forgot. Now, the F orbital. Remember those bottom 2 rows of the periodic table? They are really unusual. First off, Find LA, element 57 on your periodic table. Now go one element over. What element number is the next element over? Is it element 58? Does it just go up by 1? No, it's element 72 that's right next to it. The F orbital starts on 58. So notice how there's like a star right above your LA on your periodic table? That's trying to say it's now time to take a little detour on our trip of the periodic table. Go from 57 down to 58 here. So notice if you look at that first F row across, 58 through 71, now you go back up to hafnium, which is element number 72. And if we thought the periodic table was unusual in shape before, not rectangular, and we plugged in 58 through 71 in that chunk there, it'd be even weirder and longer in shape. It's one of the reasons why they just cut it out and put it at the bottom. Now what I notice, or what I note on here, is that the F orbital is even larger than the D. So remember how we went from 4s to 3d? Well, there's a 2 energy level jump back when you're dealing with the F. And what I want to show you, as I note here, is just the last part of the orbital notation for GD. So this is also on your note sheet. So we are going to show you orbital notation, but only the end of it for GD. GD is element 64. Now, what I'm going to do is I'm going to go to the previous noble gas. I'm almost going to blend together orbital notation and shorthand electron configuration. So, again, can I get eyes over here on this periodic table? To find the previous noble gas, end of the line, 64, 62, 58. Xenon is the previous noble gas. Okay? So I'm going to kind of blend together shorthand notation and orbital. Here's XE. And now I'm going to write down orbital notation. If I start with XE, I now need to write down for cesium and barium. What energy level is cesium and barium at? What number do you have next to cesium? 6. What letter is the orbital for cesium and barium? What orbital? S. So, actually I'm just going to go here, 6s, up and down. That gets me to element 57, which is LA. What energy level is LA in? 5 and D. So 5th energy level, D orbital, and it's the first element. So whenever I have to write out a D, I have to show my 5 suborbitals. It is the first element in the 5D. But why the F orbital is so unusual is after that first electron in the 5D, I have to jump from 57 down to 58, which is in the F orbital. What big number do we have in front of cerium in the F orbital? A 4. This is going to be 4F. And there's 1, 2, 3, 4, 5, 6, 7 suborbitals in the 4F. GD is element 1, 2, 3, 4, 5, 6, 7. One, 2, 3, 4, 5, 6, 7. Okay, this is previous noble gas xenon and the outer shell for GD. Okay? Again, I understand arrow's kind of weird. If nothing else, try to read your periodic table. Okay, another one. NP. Neptunium. That is element 93 on the periodic table. So, what I'm going to do right now is the electron configuration, not the orbitals, the up and downs, the electron configuration all the way to Neptunium. And remember, if we can do to element 93, we should be able to do any element before them, because we build up every time. And every time we start the same, 1s2. I'm going to fast forward here a little bit, not talk you through every bit. I'm going to take a breather at calcium, though. 2s2, 2p6, 3s2, 3p6, 4s2. And hopefully that makes sense. That gets us to element 20, which is calcium. We have to get to element 93. After calcium, we hit that scandium row across. That is 3d10. Connor asked about this then a second ago. After zinc, we have to get to the end of that row. The p orbital, though, we go back up to 4. 4p6. So if I stop right there, that would be the electron configuration for krypton, element number 36. Let's go to the fifth row, starting with rubidium. 5s2. Okay, treat it as a pattern. Treat it as reading your periodic table. What comes after 5s2? 4d10. What comes after 4d10? 5p6. Now I'm running out of room, so I'm going to continue on the next line down. Again, you judge how you need to. 5p6 got us to xenon. Six s2 should be next. After 6s2, we get to La. La is 5d1. After La, we have to go to element 58. That is in the F orbital. 4f14. Right now, up on the board, we have 71 electrons shown for element 71, which is Lu. Again, we want to get to 93, so we're not there yet. Remember, after element 71, we have to go to 72 and finish off the d orbitals. However, let's have eyes up on the smartboard here for a second. What I do not want you to do is this. Well, I'm covering the other 9. That's not how we do it. You're not going to write the 5d twice. Instead, realize that you're going to get through all 10 of those d's. I'm just going to change my 5d1 to a 5d10. Okay? That got us through mercury. After the 5d10 should come 6p6. Now, ladies and gentlemen, don't worry what order you put your D's and your F's in. If you flip them around, it's perfectly fine. Some people will just put 4f14 and 5d10 after the 6p6. I'll accept either version. After 6s2, after 6p6, we get to 7s2. And that gets us to radium, element 88. We are almost there. After 88, we have to do 89, which is 5d1. I'm sorry, 61. And then we enter the 5f. Now, I Neptunium is the 1, 2, 3, fourth element. This would be the electron configuration for Neptunium. What I'd like to do is give you just a couple minutes right now for the bottom two questions on this side, and then maybe a couple more for the few problems on the back side, where you're writing either electron configuration or shorthand notation for some of the examples that are given there to you. So, what I'd like you to do right now, no matter where you're at, is underneath on your packet where it says exceptions to the pattern, it says write the shorthand configuration for chromium. So I'd like you to answer that one space right now underneath where it says exceptions to the pattern. What's the shorthand notation for chromium? Chromium is element number 24, if you can't find it on your periodic table. And element 24 is chromium. Hopefully you wrote down AR in brackets, 4s2, 3d4, correct? Okay, now, ladies and gentlemen, my best gift to you today, even though I'm throwing a lot of stuff at you, is let's take a closer look at your chromium entering the periodic table. You see where it says CR? Look directly below it, between the name chromium and the symbol CR. And do you know what you're looking at right now? You're looking at the shorthand notation for chromium. Now, two things to note on this. One, the shorthand notation for every neutral atom on your periodic table is listed already. That can be used to your advantage an awful lot in this class, ladies and gentlemen. Secondly, I want you to write down that shorthand notation on your next space on your packet, where it says to write down the shorthand notation as written on your periodic table, which should say argon, and I don't care the order of what comes first, the D or the S, 3d5, 4s1. There's a difference. You were just taught 4s2, 4d4. I'm sorry, 3d4. But the actual correct answer is 4s1, 3d5. Not everybody got through that page before we started notes. I was trying to describe what the octet rule is. The octet rule is the idea that if you have a full outer shell of electrons, which means your electron configuration is like a noble gas, you are stable. The problem is, elements in the middle of the periodic table are a long way away of gaining or losing electrons to get to that stability. So instead, there's other ways that they gain stability. Now, we don't ask that you really explain this. However, that difference, as I'm showing on my note slide right now, is when a d orbital is half filled, it's more stable than if it's 4/10 full. So on your example, you wrote down 3d4. That means 4 out of the 10 is full. However, it's supposed to be 3d5. 5 out of the 10 is half full. And notice what happens to the S then. The S is now half full as well, 1 out of 2. Half-filled orbitals are more stable. Now, this occurs for two elements in that d orbital, chromium and MO. So notice on your note sheet where it says orbital stability, atoms are most stable when orbitals are either full or half-filled. Electrons will move between orbitals in order to achieve all full or half-full orbitals. We would like you to write down right now on your note sheet the shorthand notation for both CR and MO. In other words, know that column. So again, there is a blank on your note sheet right here that I want everyone to fill in by looking at their periodic table for CR, which is element 24, and MO, which is element 42. So those two elements, it's a little different for the pattern. Heck, some people might even on their periodic table put a big asterisk above CR just to know, hey, this one's a little weird. But remember, the shorthand notation is on your periodic table. Use that to your advantage. Now, granted, that's for a neutral atom, not an ion, but still, use that to your advantage. Okay. We have to continue with half-filled. Copper is element 29. Look at your periodic table right now for copper, element 29. Copper is the 9th element in the 3D. However, it's not called 3D9, is it? It's called 3D10, right? One of those 4s electrons instead is a 3d electron. That fills the d and makes the s half full. So a full 3d and a half full 4s is more stable than what we would normally say. So just like I had you write down CR and MO examples on your sheet, because those are a little unusual, I need you to do that for copper, silver, and gold right now as well. Because that column as well bucks the pattern that I've been showing you. So go ahead and take a minute to fill in that table at the bottom of your sheet. Look at the shorthand notation for element 29, Cu. Write down the shorthand notation. Do the same for silver, which is element 47, and gold, which is 79. As you are filling that in, I made a note here on the bottom of my slide, so I'll just talk while you're writing this down. My note is that the F orbital has a similar pattern with these half full and things like that. However, we are not going to have much of a focus on the F orbital. We're going to focus instead on the D orbital. And I do have a typo here where there's only on the 5D orbital elements. So that's a typo where it shouldn't say 60 orbitals, there's 5, because you have 5 things on that table above. We ask that you follow the pattern that I just taught you. However, for those 5 elements, realize the pattern is a little goofy. But you can always look at the shorthand notation. So again, all their elements will write as building up. Because we don't focus as much on the F, we have one slide to go. We've gone over D orbital. Now we have to go over D orbital ions. First off, anything in the D, you're going to find out is going to have a positive charge. That means they're going to lose electrons. And again, we'll dig deeper into why some things gain, some things lose next class period. But it has to deal with that idea of stability. And if you can get to be like those noble gases, that far right-hand column, you are more stable. That's our octet rule. Electrons are always lost from the outermost shell, because those are the ones that are furthest away from the nucleus. There's less attraction there. So what I'm going to do is I'm going to show you examples dealing with iron. So if you flip to the back page of your packet, these are the examples I'm going to go over. And what I suggest is to start writing it out neutral and then taking it away. So I'm going to do the shorthand notation for iron. Argon is the previous noble gas. 4s2, 3d6. If it's Fe plus 2, what I would do is first just write down the same as Fe. Ar, 4s2, 3d6. But then, a plus 2 charge means it lost 2 electrons. We have 2 locations here. We either have the 4s or the 3d electrons to choose what it's going to lose from. Now, when I say choose, that doesn't mean it's your decision of where it comes from. That means which of these 2 options is correct. The 4th energy level is further away from the nucleus than the 3rd. Remember, the nucleus has positive protons in it that are attracting the negative electrons. The further you are away from what you're attracted to, the easier it is to lose. This is when Ms. Knapps gave it a little analogy of you always have to take off the outermost layer of clothing when you're getting undressed. You can't take off your socks until you take off your shoes. If Fe plus 2 means it's iron that lost 2 electrons, it's going to lose these 4s2. Argon 3d6 would be the electron configuration for Fe plus 2. Last example on this sheet, Fe plus 3. I'm going to, again, start by just writing down neutral iron, which is argon, 4s2, 3d6. This needs to lose 3 electrons because it's a plus 3 charge. Well, the first 2 are going to be the outer shell, the 4th shell. Remember that fancy term, valence. There's 1 more electron that has to be lost. It must be from the 3d. So no longer is that 3d6. It's 3d5. Now again, if you can kind of figure it out by looking at it, and you want to make it look a little bit nicer, notice how I have a big space in there. You could just write it as argon 3d5. That's one of the reasons why your shorthand notation on your periodic table does it in numerical order. It puts the 3d's before the 4 s's. Because then it can help you decide I should lose the 4 s's first. There are practice problems on the rest of this sheet. We have a few minutes right now for you to work on this, probably more individually, and I'll walk around as you're working on it. But ladies and gentlemen, this is all of it. We practice it for homework. We'll practice it more at the start of next class period. But knowing how to map out electrons is a skill we have to be able to do. Okay?